Hello again. It's your friendly heavy physics teacher with another lesson for my college physics and Regents physics classes. Okay. Today we're going to be talking about colors of light and pigments. And this is my chance to get science-y about something from art or to get artsy about something from science. Sorry about that. Okay, so for the college physics guys, it's Unit 11, Lesson 2, and for Regents Physics, it's Unit 12, Lesson blank. Lesson 2. Sorry, I forgot to write that in there. Okay, just a moment. Now, let's recall how we see, all right? How we see is through the electromagnetic spectrum. Our eyes have evolved to be sensitive to a certain small range of frequencies within that entire spectrum, okay? And it ranges from about 440 terahertz on the low end to 780-ish terahertz on the upper end. So that'd be 4.4 times 10 to the 14 hertz on one end and 7.8 times 10 to the 14 on the other end. Okay, but remember, that's a very small part of the entire visible spectrum. Within that range of frequencies, our eyes differentiate the different frequencies by allowing us to see different colors. 440 to maybe 460 is deep, dark red. 460 to 480, now we're talking a brighter red, the red that we commonly think of as red. 480 to 490, now we're talking red orange. 490 to 500, now it's more orangey. And as you move up that frequency scale, you're going to move up the spectrum of the rainbow. Red, orange, yellow, green, blue, violet. Okay? So low frequency is red, high frequency is violet. All right? And how our eyes perceive that is limited because we only have two types of light sensitive cells in the retina of our eye, and one of those types of cells has three variations of it. It is that three variations group of cells that determines the color we see. Make sure you look at the notes for what I talk about with those cells. The rod cells of our eye are sensitive to light level. And the brighter it is, the less information our brains take from the rod cells. Okay. Now, my rod cells are telling my eyes right now that I've got groups of dark area behind me, groups of light area behind me, but overall, the brain isn't using that information very much. If I had very little light in the room, then my brain would be using the limited information from the rod cells to really make out what's going on in the room, if at all. Okay. The cone cells, on the other hand, the cells that are responsible for sensitivity to frequency, they're the ones that take over when the light gets brighter. They're the ones that let me know that right behind me over here is an orange book, while kind of above it is kind of a red book. There's a red book right here. There's a blue one right over here, kind of, and so I can see those colors because the light is now bright enough where the cone cells are stimulated and they're sending information to the brain. Now, the part of the brain that does the seeing is actually this part back here, right across the back. This is the visual cortex. It's part of the brain that is the occipital lobe, which is one of the reasons why if you get hit in the back of the head, you see stars, because that is the part of the brain that does the seeing. The optic nerve comes from the back of the eye. It actually crosses over in the brain, okay? and then it stimulates the visual centers back here in the visual cortex. Okay, and so that's the physical how we see. The energy goes in, stimulates the cells, and then the cells pass that information along the optic nerve into the brain, and the brain starts doing its pattern recognition. Okay, if you were to show this to an infant child, this means nothing to them. All they see is light and some areas of darkness. We have to learn to recognize pattern. We have certain instinctual things that we know about patterns, okay? But our brains have to learn patterns. And as we get better at pattern recognition, then we are better able to survive in our environment. Today, the pattern recognition we're going to be talking about is color recognition. Okay, colors of light. All right, we see color because of the cone cells in our eye. All right, we have three major type of cones. Well, we have only three type of cone cells. All right, we have cone cells that are red sensitive, meaning that they are sensitive to the range of wavelengths from the near infrared, the visible part of the last part, 440 terahertz, up into the yellow frequencies. Okay, so a red cone cell in your eye is one that's sensitive to this range of frequencies. Now, there's a certain overlap between the red cone cell and the green cone cell. Green cone cells are sensitive to the frequencies. They become stimulated when the energy from the middle of the yellow frequencies through the green into what we call aqua or cyan. All right. And so the range of frequencies from the middle of the yellow all the way through green into the aqua or near blue are what we would consider or what are stimulating the green cone cells in our eye. The blue cone cells are from that aqua range, that near green blue color, all the way through the violet to the near ultraviolet wavelength of 780 terahertz. Okay, so three cone cells in our eye are responsible for the range of frequencies that we can see, and they are responsible for letting us know what color of light is sensitive to the eye. Okay, before we really get into what colors are there and what colors are apparent to us, we have to talk about how materials affect light or are creating light. Okay, so if a material is considered luminous, it is a light source. All right, so the 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 computer screen right here that my hand is coming in toward is actually a light source. Your computer screen, I'm wiggling mine, your computer screen is actually emitting light. It is luminous. Okay? Now, this board is opaque. All right? It is reflecting most of the light that's hitting it. That's why it's white. Now, the parts of the board that are not reflecting light are absorbing it. So this word opaque, technically you're not seeing it. You are seeing the board that's around it. Why? Because it's black. Black is a color that is absorbing all light. Think about what you would see if no light was reaching your eye. If no light reached your eye, it would be perfectly dark. All right. If you've ever been to Howe's Cave and done the boat ride down in the cave, they take you to the end where the waterfall is, and then they turn the lights out, and they let you know that that is the blackest time you can ever see because there are no photons of light. down there. They've gone around a corner. All the light's gotten absorbed. You wave your hand in front of your face. You don't even know it's there. You can only feel the air of the passage. That's how black can be. All right. If I had a pure black drawing on this, you wouldn't actually perceive it. It would appear like there's a hole in here, and it goes deep inside it. That's what pure black is all about. Okay. Now, if light passes through a material and there's very little or no change to it, we call it transparent. Window glass is transparent. Clear plastic wraps are transparent. You know, water, thin amounts of water are transparent. Like a glass of water is transparent. You get a thick amount of water, it's no longer transparent, it's translucent. Translucent means that light goes through it, but it'll go through it with either a certain amount of absorption or scattering, or in the case of water, you get both. Okay? And so a translucent material will probably appear a certain color based upon what was absorbed by it and what it let go through it. Okay? Paper is translucent. It scatters a lot of the light that hits it. Some of that scattering goes through the holes and through the small spaces in the fiber of the paper. You make a paper thick enough and it becomes opaque. All right? So 4 different ways we can think about how materials affect light. Luminous, they are a light source. They are emitting light energy. Opaque, reflects light. Transparent, light goes through it. All right, so it's absorbing the energy, but it doesn't do anything to it other than slow it down for a little bit, and it emits it on the other side. Windows, okay. Translucent, absorbs the light energy, lets a lot of it through, lets some of it through, can scatter some of it, will absorb some of it. And that's why translucent materials often have colors associated with them. Okay, now to the artsy part of this area of science, or to the sciencey part of art. Okay, we're going to talk about color mixing, and color mixing with light, with luminous materials. Okay, this sort of color mixing is known as additive, because as you add more and more colors together, it creates more and more energy. To the ultimate extent, if you put all the colors of light together, you get white light. All right? So, because our eyes have 3 cones that are responsible for all the possible wavelengths of light, being sensitive to all the possible frequencies of light that are reaching our eye, we say there are 3 primary colors of light: red, green, and blue. And it's an interesting fact that if you take a red LED and a green LED, you place them very close together and you stand far enough back from them, you won't see red or green, you see yellow. All right? If you take a magnifying glass to your computer screen, okay, you can't see my hand because it's going out of view. If you take and look at your computer screen on the white part of the computer screen here, okay, you are going to be seeing very small pixels. And each of those pixels is going to be one of 3 colors: red, blue, or green. And the parts of the screen that you see that are white, all 3 of them are on equally bright. On the parts where it's black here, on the parts back here where it's yellow or orange or blue, or over here where it's brown, okay, those you're going to see different levels of brightness from those pixels, okay? So if you have a pure red light and a pure green light, mix them together, you will get yellow light from it. All right. If you want orange, it's got to be brighter red, less green. If you want more of a pale green or a yellow green color, you want less bright red, more bright green. Conversely, if you take pure green light and pure blue light, mix them together, you get cyan. All right. Cyan is an interesting color. People often call it aqua. All right. It is the blue green color of pure ocean water. For those of you who have been to on cruises in the Caribbean, that is the color. That's cyan, the color of the water in the deeper areas of the Caribbean Ocean. That is the color of cyan. All right, and that's because the salt water is absorbing pretty much all the other colors of light except for the blue and the green. All right, and the blue and the green get scattered back to our eyes, and we see that as the cyan. Now, an interesting consequence, our eyes invent magenta. There is no wavelength, there is no frequency for magenta because red is at the short or the low frequency end of the spectrum. Blue is at the upper end of the spectrum. And when you mix red and blue together, our eyes are going, wait a minute, we're receiving two different levels of energy. This is kind of weird. I think we're going to make up a color and call it this. All right. Magenta, the color we perceive as magenta, it's a real color. Believe me, it's a real color. But if you were to put it through a spectrometer, magenta would not have a wavelength. All right, it would give you a mixed wavelength, equal red and blue for it. Okay, magenta is kind of you could consider it a pinky purpley kind of color. Like I said, you mix all of these equally, you get white light. And the reason we know that is Isaac Newton, way back when, took a prism. I mean, we've been using prisms for the longest time, but he took a prism and he separated sunlight into the rainbow. Okay, you know that happens. You know, rainbows happen naturally. Okay, but then he took that rainbow and put another prism in front of the red part of it, and the red would not separate farther. But if he put the prism in front of the whole spectrum, he could get it to come back together and reproduce as white light by reversing the prismatic effect. Okay? And so white light is the combination of all the colors of light. And that's why you need white light in order to see the best arrangement of colors, say, of my bookshelves. Okay? And, you know, all the different colors that you can see from the backs of the books is because this light source up here is providing pretty much a broad spectrum of all the possible wavelengths. Our eyes perceive that as white on something that reflects all of the frequencies, and we perceive it as a color on something that is absorbing everything but the color that it is. And that's what we mean by opaque. And that's what happens when we talk about pigments. All right, pigments. Pigments are opaque. Pigments are materials that you usually use to cover something else, like a paint, or they are dyes that you actually coat something with, and the dye soaks into and physically changes the color of the material itself. Okay, but in any case, that creates an opaque situation. And the opaque situation means that it's reflecting the color that it is and absorbing everything else. So because of that, we consider pigment color mixing to be subtractive, meaning that if you put more and more colors together, you get less and less light coming off of it. You are subtracting something from the light that's hitting it and reflecting only a small portion of what's coming back. So your primary pigments are the pigments that can reflect the most amount of light. Interestingly enough, a yellow pigment will reflect red light. A yellow pigment will also reflect green light. Yellow and green light make what color of light? So a yellow pigment can reflect yellow and green light, except that if you shine red on yellow, it appears red. If you shine green on yellow, it appears green. If you shine a source of light that has red and green in it, we see yellow. Okay? A cyan pigment. A cyan pigment is absorbing red wavelengths, which means that it's reflecting blue and green light to our eyes. All right? So if white light is hitting a cyan material, it's absorbing the red, reflecting the green and blue parts. If you have just a green light shining on cyan, you see green. If you have blue light shining on cyan, you see blue. If you have red light shining on cyan, you see black. It appears black. The cyan is absorbing the red. Same thing with magenta. Magenta would reflect red light. Magenta would reflect blue light. If both of them are getting equally reflected, we see the true magenta. If blue light is hitting a magenta object, we see blue. If red light is hitting the magenta object, we see red. If green light hits a magenta object, it's black. The magenta is absorbing that. So, if we mix the pigments, if we mix yellow and cyan, we end up only seeing green. All right? And so if you take yellow paint and mix it with cyan paint, you get green paint. Honest and true. Think about the colors that go into color printers. They are not red, blue, and yellow. They are yellow, cyan, magenta. Those are the color inks that are in your color printers. Okay? So if you want a green color on your page, the yellow ink plus the cyan ink get mixed on the same spot on the page. The result is the yellow is absorbing the blue. It's reflecting red and green. The cyan is absorbing the red. It's reflecting blue and green. But since the yellow absorbed the blue and the cyan absorbed the red, what color is left over? Green. And the same is true for making blue. Cyan plus magenta results in blue because the only thing that both of these can reflect are blue. The only thing that both yellow and magenta are reflecting are red. Okay? If you mix all of these together equally, can it reflect anything? No, because pigments are absorbing some part of the spectrum. If you mix them all together equally, they are absorbing all the parts of the spectrum. Thus, it's called subtractive, because if you mix them all together, the result is black. So, there we have it. How we see color, and then how we can use color in order to see and appreciate the wonders of the world around us. Artists are doing that all the time. And because I personally know all of that, every time I go to the Clark Art Institute, every time I go to Mass MoCA, I am enthralled at the science that is being displayed by the artist's rendering. Have a great one. This has been your friendly heaven physics teacher. Go to the art museum and do some science.